symmetry. So you might think that this is immediately game over for these arcs, and that they'll reconstruct into some kind of more conventional looking surface state. So the situation is actually a bit more subtle. So as the arcs approach the bulk where they come close to each other, they're actually retreating into the bulk of the sample. And so this crystal symmetry breaking, which is only active at the surface, is becoming less and less effective. And so actually this corner feature that I've drawn here exists over some finite range of surface parameters. And if the surface symmetry breaking is sufficiently strong, but there's some finite strength required, it can reconstruct into this kind of surface state. But as she was mentioning, there's an important topological constraint on the existence of surface states. And you can roughly think of it as the way we get this Dirac semimetals by inverting some S and T bands. And they'll cross in some ring. And since it's a spin-orbit coupled system, this ring will be lifted almost everywhere except due to this axial rotation symmetry, which keeps 2 points here. But up to this last part of the sentence, everything I told you is a recipe for a topological insulator. And you can convince yourself that actually the topological invariant that you get by this band inversion is not affected by having some extra gapless points on the edge, but there actually will be a topological insulator kind of surface state. And the thing is that it may or may not intersect the nodes, but when it does, it kind of sticks to the bulk Dirac nodes over some finite range of parameters. And additionally, you can see that if you start with this TI-like surface termination and dope, eventually the TI surface will run into the bulk Fermi pockets, and I'll get this arc kind of termination instead. So it's very relevant to think about Fermi arcs in this system. So there are basically three origins for this surface, three possible origins for the surface space. So one is this arc-like termination, where the surface states run into the bulk pockets and not into each other. And there we would expect some wild-like quantum oscillations. Another possibility is this just having an ordinary 2D, well, almost ordinary, but helical TI-like surface state. And the last is that if the chemical potential is, say, up above this Dirac region, then the origin of the surface state would have to be something conventional and non-topological, say from band bending at the surface. So one suggestion against this third is that we see these surface oscillations on many different crystallographic orientations in many different samples. So it suggests some kind of robustness to this quantum oscillation. So I'll focus on kind of distinguishing between these two states in the orbit. So the first gross thing you expect is that if I make the device too thick, the surface oscillation should go away. And indeed it does. So they can fabricate devices of various thicknesses. And the surface component of oscillation here in the SFT plot, you can see it dying pretty quickly. It fits reasonably well to some exponential with some characteristic length scale of, say, 600 nanometers. So theoretically, we expect that any kind of quantum oscillation phenomena is suppressed by some Dingle factor, which is basically inversely proportional to the cyclotron frequency times the scattering time. And so here, the effective cyclotron frequency times scattering time is basically the time it takes to complete the orbit and the scattering time for each segment. So there's two pieces. The first is this bulk part, and the second is this bulk part, which depends on the thickness, and the surface part where you're sliding along the arc. And importantly here, there's some subtlety of what's the correct scattering time to phase the quantum oscillations. And on the surface, and in conventional oscillations, it's actually just the full scattering phase. Every scattering process is C-phase. In the bulk is a bit more subtle because you're kind of riding on this chiral lambda level. And this chiral lambda level doesn't turn around for anything. So it can just ride straight through disorder. So the time it takes to go through the bulk, if I'm sticking on this chiral lambda level, is independent of what the impurity potential. So the only thing that can scatter me in the bulk is if I can turn around to some non-chiral state. And that, in the regime where I'm seeing bulk quantum oscillations, requires some sizable momentum transfer. So this bulk scattering time we expect to be more like a transport scattering time, which these materials is much longer. And in fact, we can extract the transport lifetime by looking at some finite size effects in the magnetic field. So if we apply the magnetic field not perpendicular to the surface, but along the parallel to the surface, the bulk orbit, if the cyclotron radius is small, they just go like this. But if the cyclotron radius is big, at weak fields, they'll kind of hit the edge before they complete a cyclotron orbit. And right at the point where the cyclotron orbit is kind of half as big as or twice as big as the sample, you get maximal kind of backscattering from this effect. And you can see an enhancement, which just depends on thickness of the resistance, just a smooth background. And by fitting this, you can extract that there's a mean-free path of the transport mean-free path of roughly 1.2 microns, which is in good agreement to actually twice this characteristic decay scale. And the twice comes from the fact that you have to traverse the bulk twice in order to complete this orbit. So one caveat is that there's some subtlety here, which is that you're looking at two thermal resistance here, and so really bulk and surface are kind of intermingled. We want to distinguish this kind of thickness dependence with some trivial kind of geometric factor with the bulk just shorting out the surface. So you can try to decay fits slightly less well to power loss and thickness decay that suggests like this, but this is really kind of a quantitative distinction. So can we do something qualitative? This is where Philip had a really cool idea, which is to look at not a rectangular device where both surfaces are parallel, but a triangular device where there's some angle between the two surfaces. And now if I apply a magnetic field, the kind of effective thickness depends on my position along this triangle. And if you recall back to the first part of my talk, the frequency of this quantum oscillation doesn't depend on the thickness of my sample, but the phase of them does. And so this is a lot like having, say, a Josephson junction in a magnetic field, where the orbits from different parts of the sample have different phases, and they all are expected to wash out and kill each other. Whereas if I have parallel surfaces, they add up coherently and give me these quantum oscillations. And indeed, you can see that if you look at this triangular device, these nice bulk oscillations, and the surface one is just completely gone. And importantly, this triangle device was fabricated to have the same surface bulk ratio as this rectangle device within, say, 10%. And so this is not a trivial, different surface to bulk volume ratio effect. And also, the way this triangle device was not made by kind of rastering the focused ion beam around to carve deeper and deeper as I go this way. Rather, they tilted the sample with respect to the ion beam. So the ions were always coming in at grazing incidence to every surface on this triangle, all three of them. And so we expect that the cleanliness of this triangular surface to be similar to the rectangular one. And so this is really suggestive of this arc-like termination, because it relies on some kind of phase coherence of the thickness of my sample. And another kind of more detailed effect that we expect of these kind of non-local Fermi arc-like quantum oscillations is that as the electron slides along the surface arc, it doesn't actually reach the end of the arc before it jumps into the bulk. But if you look at kind of non-adiabatic corrections to this semi-classical picture, you find that the electron actually jumps into the bulk when it reaches, say, an inverse magnetic length of the surface. So actually the arc length that you have to slide across depends on field and becomes shorter and shorter as you go to stronger and stronger field. And what this means is that actually the position of these peaks is not regularly spaced with Landau level index, but kind of slides down as you go